All right, what I want to do is go over the third kinematics problem in the packets that I've given you. Basically, what we want to do is kind of develop, I would say, a process that we want to follow in order to maximize the amount of points that we get on the test, specifically on a free response question. So if you take a look at this problem here, you got a person and they're here, they're going to kick a ball at an angle, and then there's a fence all the way at the end of it. That fence is 2.5 meters high. It's 32 meters away horizontally, and we are told that this thing leaves at 20 meters per second, and the angle is 37 degrees with respect to the horizontal. And another thing that we're told in the problem is that the mass of the ball is 0.5 kilograms. Now, what we're going to see is, based on the information they give us, we should be able to attack this problem step by step. The other thing is that we're given an impact time right here, and that impact time is 0.05 seconds. And that's going to tie into the first problem, which is problem A. It says, determine the magnitude of the average net force extended on the ball during the kick. So I understand we're in kinematics. I also understand that we're kind of reviewing forces here. But at the same time, all these questions that you can be given are cumulative in nature. So you're going to see a lot of overlap, and you're going to see us go into other topics, which isn't a bad thing because we're planning to review them all anyway. But right away, what we have here is we have some sort of force being applied to the ball at that angle, and that lasts for a certain amount of time, 0.05 seconds. So we don't know the average force. The impact time is 0.05 seconds, and this is a classic impulse momentum theorem problem where, in raw form, J equals delta P. So I would either write that, or I would write this, some form of the impulse momentum theorem. And this is usually the one that people are most comfortable with. But you got to do something to justify that you know what you're talking about here. And the very first thing you can do in a problem like this is write out the raw equation in variable form. Don't just write the numbers. Write out the equation. You got all the time. You don't have all the time in the world, but you got enough time to do that, right? And so what we end up doing is then putting in the numbers. Well, that's unknown, so I'm going to leave it as a variable. The time, the impact time, 0.05 seconds. And the mass is 0.5 kilograms. The final velocity is actually 20. Initially, it was 0. So there's our math there, and we can get our answer pretty quickly here. You're going to find more often than not the numbers are pretty easy to work with on this test. So that shouldn't really be hindering anybody. And what I get is an average force of 200 newtons. That's what's going to get the ball from rest to that speed right there, 20 meters per second. And basically, I haven't looked at the rubric in years, but if this is a possible 2 points, I'd say this is 1 point, and then this is the other number and the unit. You're going to find that they do actually prefer you to adhere to sig figs, and if you actually look at this, I'm seeing 2 sig figs in just about every quantity here. So what you can usually do, you could leave it like this. They're not going to really do anything about it. But if you were looking to put a number like this in the sig figs, 2 sig figs, it would be 2.0 times 10 to the 2 newtons. When you look at the coefficient, that tells you how many sig figs there are. So a lot of people are uncomfortable saying, oh, that's 2 sig figs, because, based on what you learned in chemistry, looks like 1 to me the way I have it written there. But if I write it like that, that is 2 sig figs right there. Not totally necessary, but if you're keeping track of things to do, you might want to do that. And I would say usually you won't run into that issue all too much in the exam where you just go, wait, that looks like 1 sig fig to me. Is that okay? After that, we're asked to determine the time it takes for the ball to leave the fence. So this was problem A, right? Problem B, this thing is going to follow a parabolic trajectory it's a classic. Let's make sure you can actually see the parabolic trajectory. It's a classic 2D projectile motion problem. And so we need to do this in steps here. And the golden rule of projectile motion was always be in your components here. So we're going to have to break that down into the x component, which is Vx, and the y component, which is Vyi. This is an x problem, so we're really interested in Vx here. So that would be 20 cosine 37. Let's make sure I'm in degree mode before I do this. I am. And I get 15.97 meters per second as my speed. Now, just going into your two-dimensional motion here, you can write this. This is probably a point in my book. We're just writing that right there, and then we can put in our numbers. 15.97, and then this would be t. We don't know how long that is. So that's what we're looking to find here. So 32 divided by that is, if we take a look, the time is 2.003 seconds. But we're running into the issue here. If I'm trying to keep the 2 sig figs, great. 2.0 seconds, I'll round it. It looks a lot better now to me. If you take a look at C, it says, will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the fence will it pass? So basically, we know that it's 2 seconds when it reaches this point right here. And so what we want to do is find out what the vertical displacement is right there at that particular time. So we'll take the 2 seconds and bring that over to the y direction. We do need the y velocity here, so maybe we can just go back here and solve it really quickly. 20 times sine 37 is going to give me 12.036 meters per second. You know, so, I would say, a good habit, and I've been telling you this all year, is, round as little as possible, and you can round your final answer to whatever you need it to be. And you won't run into many issues there. So basically, we have an initial vertical velocity of 12.036 meters per second. The VYF at that point is completely unknown. Delta Y at that point is completely unknown. We said that the time is going to be 2 seconds, and the acceleration is that due to gravity. So we have 3 out of the 5. We can get all 5. Just taking a look at the quantities I'm given, looks like this is going to be the formula to use. Again, this right here is 1 point justification. If you don't write it, they might not give you that point. All right, because it's the same deal in class. You have to show your work leading up to the final answer. How do we know that you just didn't copy the final answer from somebody else? Especially in a take-home test, especially in a test where you're taking the AP test and you're not supposed to be talking to your friends, right? Because you wouldn't do that. Delta Y, don't know what it is. 12.036, 2, 1/2, negative 9.81, 2 squared. Got all our numbers here. And let's see what we end up getting. Alright, now if I type them in correctly, let's see. I get delta Y equals 4.45 meters. So the question literally said how far above. It was 2.5 meters high, the fence. So obviously the numbers that I'm getting, it's above it. So 4.45 minus 2.5. When we get our answer here, that's about 1.9526 meters. But again, I'll go to 2 sig figs. You could write 1.95 at 3 sig figs, or this would round up to 2.0 meters. After that, we're asked to sketch the horizontal velocity components and the vertical velocity components. So essentially, what you want to have is the horizontal velocity should be a set value, right? If we were doing Vx as a function of time, it was just the 16 meters per second, or approximately 16 meters per second. So I would expect it to be a straight line. With respect to the other one, Vy as a function of t, we're going to start at the 12, and then let's actually just solve for Vyf to see where this graph should end. So if I did that, Vyf equals Vyi plus negative g times t. I could plug in those values there, 12.036 plus negative 9.81 times the 2 seconds. I get negative 7.5. So this thing will dip below the x-axis, probably somewhere around there. And I would expect this slope to be equal to negative g. So, you know, you're given a grid there, and your graph should look something like this, where, you know, we should start at around 12, and you should end at around negative 7.5. Let's actually make that a little bit clearer up there. And that would be how you would be more exact. Now, last question, I think it's probably something that I typed in there. It kind of looks like a different font. What was the impulse applied to the ball by the kicker? So, very conceptual question. Big trick is people have trouble distinguishing impulse from force, right? Impulse is J. The force is 200 newtons, and the time it's applied is 0.05 newtons. So if we're looking for impulse, we got to take the 200 times it by 0.05. And what do we get? I get that it is 10. You could write Newton seconds if you want, or you could be in base units here, kilograms centimeters per second. Either one would be perfectly acceptable. And basically what you're seeing here is that, you know, if each of these problems are 2 points, you can see it literally in the lines with the math. And you always, I can't stress this enough, always want to write the raw formula. And then typically what you should do after going through all of your answers is circle the correct answer in each case. That would always be, I would say, very recommendable. The other thing is you really got to try to make your work, and this is a struggle for some people. Some people naturally do it, but other people don't. Make it nice and neat, right? Step 1, step 2, step 3. Or you could do step 1, step 2, step 3. Some people do that, but make it organized. Make it so that it's something that somebody's going to follow. I swear I must spend days zigzagging through some of your work here, and I like you a lot more than they do, so I don't think they're going to do that for you, so just keep that in mind.